In this video, we want to talk about sigma notation. Now, some of this at the start is things that we've talked about in pre-calc and you've done previously, but the stuff towards the end will be things kind of combining this sigma notation with some limits and some calculus ideas that will be kind of new or combined things that we've already gone over. Now, for a sigma notation, just to refresh your memory, the sigma notation, we have the sigma, which is the capital E looking thing, and then we have the K, which goes from 1 to N. That's kind of the counter. And then with the A sub K is some formula that we have in our notation. So if we have sigma notation K equals 1 to 4 of 2K. Now in pre-calc, I know we evaluated these by just using our calculator at times. We want to make sure we understand two things here today. One is how to expand them so we understand what we're doing, but then also how to do these by hand in using the formulas. The reason is, as we move on and we're doing these, we're going to be doing the variables, and we're not going to be able to put them on our calculator. So if you remember, you start at the bottom number, which is 1, and you put 1 in for K, and you get 2, plus you put 2 in for K, which is 4, plus put 3 in for K is 6, plus put 4 into K is 8. And that is our expanded form. For the next one, we start at 3 and we go to 6. You start at the bottom number and you count out to the top. So I put a 3 in, -1, you remember, to an odd power is negative, to an even power is positive. So when I put a 3, that becomes a negative, and so I will get -9, 3 squared. When I put in a 4, I get a positive 4 squared, which is 16. When I put in a 5, I get a -5 squared, which is 25. And finally, when I put in 6, I get a plus 36. So that's just expanding the sigma notation, kind of reviewing how we did that. Now, imagine we didn't have a number at the top, we just had n. And we wanted to write this in expanded form. Now, the first thing I want you to notice is the variable here in our formula is k. So as I put the 1 in, I would have 1 over n, 2 times 1 minus 1, which would just be 1, plus, put 2 in, 1 over n, put 2 in, that's 4 minus 1, which is 3, put 3 in, that's 1 over n to the times 5, plus all the way to the n. When I put n in, I have 1 over n to the 2n minus 1. And I want you to notice as we do this that this n here doesn't change. So as we look at our series there, really I could pull out the 1 over n and have just 1 plus 3 plus 5 plus ... to the 2n minus 1. Now, what this is going to do is we look at one of our first rules of summation. This 1 over n is basically just a constant in front in the formula for our sigma. So really, we can pull that out in front of our sigma and just evaluate our sigma and have the 1 over n in front. And that's going to help us as we move forward. Okay. So here are our rules of sigma notation, and I'll give you a second to write these down. And the first one is the one that we just talked about. If you have a constant in the sigma, you can just pull that out in front of the summation notation and then just deal with the sigma. Our second rule is that if you have a plus, you can split this into 2 separate sigma notations and treat each one individually. So if we have something like this, sigma notation of 1 to 10 of 3k squared, I could think of that as just 3 and split this up from 1 to 10 of k squared. If I had sigma notation 2 to 8, I could split this up and have sigma notation of 2 to 8 of k plus, pull the 3 out, sigma notation of k is 8, or 2 to 8 of k cubed. Now, we could expand these out and try to figure out what is k squared from 1 to 10, or what is k, or what is k cubed. But to do that, we want to use some other formulas. So here are our some more sigma notation formulas. The first one says if we have the sigma of a constant, of a number, that is just c times n. And you may remember these from pre-calc. If we have from 1 to n of k, we're just adding up the numbers. Our formula is n times n plus 1 over 2, or more importantly, and for what we're going to do, I really encourage you in all of these to use the second formula, and you'll see why later, n squared plus n over 2. So if we use that formula, and we would come back here, oh, we need the next one, k squared. If we come back here for k squared, we have this formula. So if we have 1 to n of k squared, it's the first formula or the second one, which would be more helpful for us. This is 2n cubed plus 3n squared plus n over 6. And our final one is for n cubed, or k cubed, and this is n to the 4th plus 2n squared, 2n cubed plus 2n all over 4. So I'll give you a second to write those down. So if we use this one for k squared, if we came back here and we wanted to figure out what is this for k squared, this would be 3, and then based on our formula, 2n cubed, so this would be 2 10 cubed plus 3n squared plus 3 10 squared plus n all over 6, and that's how we could evaluate that sigma notation. Okay. So using these formulas will help us as we try to evaluate these going forward. Okay. So what we want to look at now is how to combine the sigma notation with our limits as n goes to infinity. So this will become important as we get into our next chapter. So we want to just kind of work at this point. I'm just going to give these limits to you, and we're going to work through them, and eventually we'll see where these come up and how we end up with one of these. So let's say we have the limit as n goes to infinity of the sigma notation of 1 to n of k over n squared. Now first, we have our limit, which is in terms of n. But our sigma notation is not in terms of n squared. So I can pull that n squared in front of the sigma notation. And I get the sigma of just k. So all of this is inside the limit. So when I evaluate my limit, I have the limit of n going to infinity of 1 over n squared. And now this is where I'm going to use my formula for k. And my formula for k, the sum of from 1 to n, is n squared plus n over 2. Now, if we look at this limit then, as n goes to infinity, we have the limit of n squared plus n all over 2n squared. And then that is the limit that we want to evaluate. Now, when we have it as one limit like this, you remember as n goes to infinity, what we really need to do is just look at the leading coefficients. When n gets really, really big, this plus n doesn't matter. So this basically becomes n squared over 2n squared. So as n goes to infinity, our limit is 1/2. Let's try another one. A little harder here. The limit sigma 1 to n. Now, we have the 4 over n here, which once again is not in our sigma. That's just a constant. So I can kind of pull that out in front. Now, I'm going to do a couple things here. One, I can split this sigma into 2. So I can have sigma k over n squared plus sigma 1 to n of 2. So I'm able to split that into 2 because of the plus. Now, this first part, this becomes k squared over n squared. But that n, once again, is not in my sigma notation, so I can pull that out, and I'm going to get 1 over n squared in the front, and my sigma notation is 1 to the n of k squared plus sigma notation the n of 2. So you can see what we're doing as we do these problems is we're trying to get down to our sigma notation just being one of these. A constant, k, k squared, or k cubed. Because once I have those simplified that far, I can now just use those formulas. So here I have the limit as n goes to infinity of 4 over n. That's still kind of hanging around out in front. I have 1 over n squared. Now, my sigma of k squared is 2n cubed plus 3n squared plus n all over 6 plus 2 to the n. Now, in this case, I have two different parts, so I can separate them with the plus sign. So this would give me the limit. So the limit as n goes to infinity. And the first part here is I still have the 4n out in front. And depending on how you do these, you may be able to kind of combine these quicker. If you're seeing how these are going to end up here, over n over 6n squared plus 2n. And then my next step is going to be to distribute this 4n to both of these. So I have the limit of n goes to infinity of, and my first fraction, I'm going to multiply by 4. So this gives me 8n cubed plus 12n squared plus 4n all over 6n squared, or excuse me, cubed, because this n goes in the bottom, plus 8n over n. Now, one of the ways to kind of check if you're doing these, on many of these, on most of these, you're going to end up with something like we have in both of these fractions, where your leading coefficients are the same power. So that means you can kind of ignore everything else, and your leading coefficients is going to be 8/6 on the first one. Your leading coefficients on the second one is 8. If you do not have the same leading coefficients, then you're either going to get 0 or infinity, which is possible. These limits will very rarely, if ever, go to infinity. So it is possible if you have something like an x squared on the bottom, as the bottom goes to infinity, that part of the whole limit will be 0. But you should always end up with some number as you're doing these. And now if we combine those, we get 28/3. So your homework has kind of two parts. The first part of it is just a review of sigma notation, using these formulas to evaluate these type of questions. And then the second part is kind of combining these and doing these limit sigma notations, where you're going to end up with something like this so that you can put it into the formula. You're going to end up with a limit that n goes to infinity, and then you're going to evaluate that limit to end up with some number as your answer.